welcome to Swecodes, Future Coding Champions. Today, we're diving deep into Leetcode problem number 2410, maximum matching of players with trainers. This is a beautiful problem that perfectly demonstrates the power of greedy algorithms and efficient problem-solving techniques. This medium difficulty problem might seem challenging at first, but I promise you, by the end of this video, you'll not only understand how to solve it, but you'll also gain insights that will help you tackle similar problems with confidence. We'll explore 3 different approaches, starting from the most intuitive to the most optimal, using greedy algorithms, 2-pointers, and sorting techniques. Are you ready to level up your problem-solving skills? Let's begin this exciting journey together. Let's understand what this problem is asking us to do. We have 2 arrays, players and trainers. Each element in the player's array represents the ability level of a player, and each element in the trainer's array represents the training capacity of a trainer. Now, here's where it gets interesting. A player can only be matched with a trainer if the player's ability is less than or equal to the trainer's capacity. Think of it like this: a trainer needs to be strong enough to handle the player's skill level. But there are important constraints we need to remember. Each player can match with at most one trainer. No sharing allowed. Similarly, each trainer can match with at most one player. They can only focus on one student at a time. Our ultimate goal: maximize the total number of successful matches. It's like organizing the most efficient training camp possible, where we pair up as many player-trainer combinations as we can. Let me show you visually how this matching process works. Look at our players on the left. We have players with abilities 4, 7, and 9. On the right, we have trainers with capacities 8, 2, 5, and 8. Watch carefully as we try different matching combinations. First, let's see if player 1 with ability 4 can match with trainer 1 with capacity 8. Since 4 is less than or equal to 8, yes. This is a valid match. You can see the solid green line. But look what happens when we try to match player 1 with trainer 2 who has capacity 2. Since 4 is greater than 2, this match fails, shown by the dashed red line. The trainer simply isn't strong enough. This visual representation helps us understand that not all combinations work, and we need to be strategic about our matching approach. The key insight here is that we want to find the optimal pairing strategy that maximizes our total matches. Let's walk through our first example step by step. We have players 4, 7, 9, and trainers 8, 2, 5, 8. Step 1. Player with ability 4 tries to match with trainer with capacity 8. Since 4 is less than or equal to 8, it's a match. Step 2. Player with ability 7 needs a trainer. We have another trainer with capacity 8. Since 7 is less than or equal to 8, another successful match. Step 3. Now we have player with ability 9, and the remaining trainers have capacities 2 and 5. Final result: we achieved 2 maximum matches. Now let's look at example 2, which demonstrates an important constraint. We have 3 players, all with ability 1, and just one trainer with capacity 10. Player 1 matches with the trainer easily, 1 less than or equal to 10, perfect match. But here's the crucial lesson: player 2 and player 3 cannot get trainers, even though their ability, 1, is less than the trainer's capacity, 10. Why? Because each trainer can only match with one player. This example beautifully illustrates that the constraint works both ways. Not only can each player have at most one trainer, but each trainer can also have at most one player. The maximum matches here is just 1, despite having a very capable trainer. This second example reinforces why we need an optimal matching strategy. It's not just about capability, it's about the one-to-one matching constraint. Now, let me introduce you to 3 different approaches to solve this problem. This is where things get really exciting. First, we have the brute force approach, represented by our snail emoji because, well, it's slow. This approach tries every possible combination of matches. While it guarantees finding the optimal solution, its time complexity of O(n) times m makes it exponentially slow and impractical for large inputs. Second, the binary search approach, our magnifying glass. This is better than brute force, using binary search to find suitable trainers. With n times m times log m complexity, it's an improvement but still not optimal. Finally, the two pointers approach, our lightning bolt. This is the optimal solution using a greedy strategy with sorting. At n log n plus m log m complexity, it's efficient and elegant. The only downside is that it requires sorting, but that's a small price to pay for such efficiency. Let's start with the brute force approach to build our understanding from the ground up. The idea is simple but exhaustive. We try all possible combinations of player-trainer matches using recursion with backtracking. For each player, we attempt to match them with every available trainer. If a match is valid, we mark that trainer as used and recursively solve for the remaining players. Look at this combination tree, it shows how we explore different matching possibilities. Some paths lead to valid combinations, while others don't. The beauty of this approach is that it guarantees finding the optimal solution because it literally checks everything. But here's the harsh reality, the time complexity is n times m. That's factorial time. For just 10 players and 10 trainers, we'd be checking millions of combinations. This approach teaches us the importance of optimization in algorithm design. Now let's look at the Java implementation of our brute force approach. Notice how we use a Boolean array to track which trainers are already matched. The backtrack method is the heart of this solution. When we reach the base case where all players are processed, we return 0. Otherwise, we have two choices for each player, either try to match them with an available trainer, or skip them entirely. See this, for loop. It tries matching the current player with each trainer. If a match is valid, we mark the trainer as used, make a recursive call, then backtrack by unmarking the trainer. This is classic backtracking, try a choice, explore its consequences, then undo it to try other options. The math.max operations ensure we keep track of the maximum matches found across all possible combinations. While this code is elegant in its completeness, remember, it's teaching us what not to do for large inputs. Here's the same algorithm in Python, and I love how Python syntax makes the logic even clearer. We define a nested backtrack function that captures the used array in its closure. Notice how Python's list comprehension and cleaner syntax make the code more readable. The logic remains the same, for each player, we either match them with an available trainer or skip them. The beautiful thing about seeing both Java and Python implementations is that it reinforces the algorithm's logic regardless of the programming language. The pattern of backtracking remains consistent: make a choice, explore, then undo and try alternatives. Now let's level up with the binary search approach. This is where we start getting clever about our search strategy. The key insight here is that if we sort the trainers array, we can use binary search to efficiently find a suitable trainer for each player. Instead of checking every trainer linearly, we can eliminate half of the search space with each comparison. Watch this visualization. For player 7, we're searching through the sorted trainers array, 2, 5, 8, 8. The binary search quickly narrows down to find that trainer at index 3 with capacity 8 is a suitable match. But there's a catch: we still need to track which trainers are already used, which adds complexity. That's why this approach, while better than brute force at of n times m times log m, still isn't optimal. It's a great stepping stone that teaches us how sorting and binary search can improve our algorithms. Let's examine this binary search implementation in Java. First, notice how we sort the trainers array. This is crucial for binary search to work correctly. The binary search trainer method is where the magic happens. We maintain left and right pointers to define our search space. When we find a trainer with sufficient capacity, we don't stop immediately, we try to find the smallest suitable trainer by moving the right pointer left. The findAvailableHelper method handles the complexity of checking which trainers are already used. This is necessary because our used array tracks assignments, and we need to find an available trainer within our binary search range. This implementation beautifully demonstrates how we can combine different algorithmic techniques, sorting, binary search, and state tracking, to create a more efficient solution than brute force. The Python implementation of binary search showcases Python's elegant handling of helper methods. Notice how we define binary_search_trainer and find_available as methods of the solution class. The binary search logic remains the same, but Python's cleaner syntax makes the algorithm flow more apparent. The // operator for integer division and the range function for iteration are particularly nice touches. One thing I want you to appreciate here is how both implementations handle the edge case where multiple trainers might have the same capacity. We always try to find the leftmost available trainer to maintain consistency in our matching strategy. And now, the moment you've been waiting for, the optimal two-pointers approach. This is where algorithmic elegance meets efficiency. The beauty of this approach lies in its simplicity. First, we sort both arrays. Then, we use two pointers, I for players and j for trainers. The matching rule is straightforward. If player, I, can be matched with trainer, j, we match them and move both pointers forward. Otherwise, we just move to the next trainer. Why does this greedy approach work? Because once both arrays are sorted, matching the weakest available player with the weakest suitable trainer is always optimal. We never need to save a weaker trainer for a stronger player later. This is the most efficient solution. It's clean, intuitive, and runs in O, n log n plus m log m, time, dominated by the sorting step. Watch the pointers I and j as they move through the sorted arrays. Step 1, player 4 meets trainer 2. Since 4 greater than 2, no match. We move to the next trainer. Step 2, player 4 meets trainer 5. Since 4 less than or equal to 5, match found. Both pointers advance. Step 3, player 7 meets trainer 8. Since 7 less than or equal to 8, another match. Both pointers advance again. Step 4, player 9 meets the last trainer 8. Since 9 greater than 8, no match possible. See how elegant this is? We never go backwards, we never reconsider previous decisions. Each element is visited at most once, making this algorithm incredibly efficient. This visualization really drives home why the two-pointer technique is so powerful for sorted array problems. Here's the optimal solution in Java, and look how clean and concise it is. First, we sort both arrays. This is the key that unlocks the efficiency of our algorithm. The main logic is breathtakingly simple. Our while loop continues as long as both pointers are within bounds. The if condition checks if a match is possible. When it is, we increment our match counter and advance both pointers. When it's not, we only advance the trainer pointer to try a stronger trainer. This implementation is a perfect example of how the best solutions are often the simplest. No complex data structures, no recursive calls, just two pointers marching through sorted arrays. The elegance of this solution should inspire you. Sometimes the most powerful algorithms are also the most intuitive. The Python implementation of our optimal solution is equally elegant. Python's multiple assignment on line I equals j equals matches equals 0 showcases the language's conciseness. The algorithm translates beautifully to Python. The while loop condition reads almost like English, while I is less than the length of players and j is less than the length of trainers. The matching logic remains crystal clear. What I love about showing both implementations is that it reinforces a crucial lesson: great algorithms transcend programming languages. Whether you're coding in Java, Python, or any other language, the two-pointer technique remains a powerful tool in your algorithmic toolkit. Now let's compare all three approaches and understand why optimization matters so much in algorithm design. The brute force approach, with its O, n times m, time complexity, is exponentially slow. It's like trying every combination on a massive lock. It works, but it's impractical for anything beyond tiny inputs. The space complexity of O, m, comes from tracking use trainers. Binary search improves to O, n times m times log m, polynomial time. For each of n players, we might check m trainers with log m binary search operations. It's better, but still not great for large inputs. Our optimal two-pointer solution shines with O, n log n plus m log m, time complexity. The sorting dominates, and the actual matching is linear. Plus, with O, 1, space complexity for the matching process itself, it's incredibly memory efficient. This comparison teaches us a fundamental lesson: the right algorithm choice can transform an intractable problem into one that's efficiently solvable. Let's wrap up with the key lessons from our journey through this problem. First, always start with brute force to understand the problem deeply. It might be slow, but it builds your intuition and guarantees correctness. This foundation is invaluable when developing optimized solutions. Second, binary search can improve performance, but added complexity isn't always worth it. Sometimes, a simpler approach like two pointers is both more elegant and more efficient. Third, two pointers with sorting is often optimal for matching problems. When you see problems about pairing, matching, or finding optimal combinations in arrays, think about whether sorting could help. Fourth, greedy algorithms work when local optimal choices lead to global optimal solutions. In our problem, matching the weakest player with the weakest suitable trainer is always the right choice. Finally, practice similar problems like meeting rooms and interval scheduling. The patterns you've learned today, sorting, two pointers, and greedy strategies, appear again and again in competitive programming. Remember, becoming a great problem solver is a journey, not a destination. Happy coding!